A transformation moves a figure in some way to create a new figure. In geometry, we focus on 4 transformations: translation, reflection, rotation, and dilation. In this video, we're going to look at 2 of them. That'd be the translation and the reflection. But before we start moving figures around, we need to cover some vocabulary. In a transformation, we have 2 figures. We have an old one and we have a new one. The old figure, the one that we start with, is called the pre-image. The one that we end up creating is called the image. Okay, so in a picture, if you have both of these drawn side by side with each other, there is a way to tell which is which, and that's using prime notation. So if we take a look at the figures that we have down here, there's a couple of triangles that we've got. The first is A, B, C. The next, you're going to notice, has all the same letters, A, B, and C, except that they have these little markings that are next to each of the letter, which is what we call prime notation. So this is actually read as A prime, B prime, and C prime. The figures that have the prime notation are going to be the ones that are the image, the new figure. Of course, the arrow kind of indicates that here for you. Okay, but the regular letters would be your pre-image, your starting figure, and then the ones with the primes would be your image or your newer picture that you got. The other thing that we got to talk about is the word congruent and what that means. For 2 figures to be congruent, they have to have the same shape and the same size. So that ends up making them identical to each other. Okay, so there's a couple examples here. I've got 2 quarters. Aside from the fact that the first has a picture of a bat and then that one's got a picture of a cow and some cheese on it, these would be congruent. They're both the same shape, which is a circle, and they're also the same size, okay? Now, a way that you can kind of imagine testing this out if you want is you take the 2 figures and you stack them, okay? And regardless of which way you stack them, whether I put the cow on the top or I put the bat on the top, if I can place the 2 figures on top of each other and you can't see the one that's behind it, it perfectly covers it, then that tells you that you've got the same size. So it would also tell you get the same shape, because they would have matched up otherwise. But you could tell from the beginning that these were both circles. Okay, so that's an example of congruent figures. Now, congruent figures don't need to be your basic shapes like circles and triangles, things like that. It could be anything. Here's a couple of protractors. These have to be congruent to each other. You know, they were molded by manufacturer to be the same size, right? And if you were to take one protractor, this one actually had upside down, and maybe flip it over, I can rotate it, whatever you need to do. So imagine that you can actually pick them up and move them around and set it on top of the other one, and it's a perfect match. Then that tells you that they are congruent. Okay, so it applies to many things, not just our basic shapes. When we do transformations, there's always going to be a question of whether or not congruency is maintained from the pre-image to the image. If it is, then we have what's called an isometry. An isometry is a transformation where the pre-image and the image are congruent. Okay, of the 4 transformations that we're going to look at, 3 of them are isometries. They do maintain congruency, but there will be one of them that is not an isometry. It does not maintain either the shape or the size. One of those things is not going to be present when we do that type of transformation. Let's go ahead and take a look at our first transformation, which is a translation. A translation moves every point in the figure the same distance and in the same direction. In layman's terms, a translation is just a slide. It's the most simple transformation that we're going to look at. It also happens to be one of, I think, the more restrictive ones. It doesn't make it hard or anything. It's an easy transformation, but it's very restrictive that when you slide the figure over into a new location, you can't rotate it at all, you can't flip it, you can't do anything extra with it. It's just like you take the figure and you push it into a certain direction, and then that's the end of it. Okay. Any figure, it does say here that it moves every point of the figure the same distance and the same direction. Okay. So what we can do is we can think of a figure like the triangle here is really just 3 points that are connected together. And if we strip away the sides that we have on here and just look at the 3 points individually, we can follow this definition. It's going to take each of these points and it's going to move them the same distance. I think that all should make sense to us how far we're moving. And it's going to move them in the same direction. So that part is referring to these parallel paths at each of the points that are going to move. So point B, to get it to B prime, is going to follow this path. Okay, so again, imagine like all the sides are just removed from there. Okay, all the sides are moved. And B is going to move in that direction. All right, the other points, C to C prime, are going to move here. And if you look at the two red lines that I drew, you're going to notice that they are the same size and they are running parallel to each other. So that's what the translation's doing. A is going to be a little bit messier to draw because it's on top of the figure, but you will also notice that the line appears to be the same length and that all three of them are all running in a parallel direction. So a way to do translations, which is a bit of a trick when you actually do this, is not to translate the whole figure, but to just look at the individual points, go ahead and translate those to the new locations, and then just connect the figure together. Okay, underneath the figures, we have this statement here, which is read as triangle ABC is congruent to triangle A prime, B prime, C prime. Okay, so that's our symbol for triangle. If you have that before the three letters, then you know that we're talking about the shape of a triangle. Right here in the middle, this is the symbol for congruence. Okay, it looks like the equal sign where it's got the two bars, but it has a little wavy figure that's above it. Okay, so in geometry, instead of using the equal sign to tell us that two shapes are the same, what we do is we use a congruent sign. So it's a lot like using an equal sign, except that the equal sign is actually reserved for numbers to show the two values are the same size, where the congruent symbol is going to be used to show that two shapes are the same. All right, for example number 1, we're going to graph a quadrilateral with the points A, B, C, D, and we're then going to do a translation by using what is called a mapping here. Okay, you're going to notice that we did write the word quadrilateral. We don't actually have a symbol that we're going to put in front of the A, B, C, D like you would see for the triangle. So not everything has symbols that go with them. Sometimes we'll just put words in front of them, but this does mean that we've got a four-sided figure that's going to have vertices A, B, C, and D that will be connected. And they will be connected in that order. That's an important thing here. That point A must connect to B, B must connect to C, and then C to D. So it's not just because they're alphabetical, but it's because the order that they're written, that's how you connect them. Okay, so we're going to go ahead and plot these points and connect those to make our quadrilateral. So here it is graphed. The quadrilateral is actually a parallelogram. In a different lesson, we'll actually talk about how you identify it as a parallelogram, but if you wanted to know, that's what the shape is that we actually created here. Okay, now what we're going to do is use a mapping. This is a mapping here. We're going to use a mapping to create a new image. Okay, and what the mapping tells us is that it really goes back to the idea that we're moving every point the same distance in a translation. So it says that we should be able to take any points that we have here, whether they be the 4 that we use to connect the figure or just any random point that happens to be on there, like this coordinate here is at 5, 0. You could also take that one. But you take any of the coordinates that are on there and you perform this thing here, okay? And it tells you that you've got to take your x's and increase it by 3, increase them by 3. You got to take your y values and decrease those by 3. Okay, so let's just take a look at A. Okay, our coordinate A is -2, 6. Okay, so we got to take our x value, -2, and we got to add 3 onto it. Now, this is going to end up creating what's called A prime, the new coordinate for A. So we can take -2 and we're going to add 3, which is going to create 1. We're then going to take the y value 6, we're going to subtract 3 from that, which will give us 3, and that is the location of A prime. All right, let's go ahead and do B prime before I actually start to graph anything here. So B prime, we're going to use 2 and 4. 2 plus 3 is 5, and 4 minus 3 is 1. So that's going to give us B prime. And now I'm going to go ahead and graph those just so that you can see when those 2 points are connected. When those two are connected, it's going to start to create the figure that we know, and it's just sliding over. All right, so let's look at where are these at. 1, 3, you go over 1, up 3. Okay, so it's going to be A prime. And B prime is going to be at 5 and 1. So that's 2, there's 5, there's 1. Once I connect those, you're going to see that it looks like the segment that we have on the top here. So the whole figure is just sliding into this location. So then C compared to B was directly 3 units underneath it. So we should expect that it's going to be there. Oh, and I don't think that I mentioned this like earlier in the video, but a translation is an isometry. When you just slide the figure over, you just push it, you're not changing any of the size or the shape that goes along with it. So you can use that as a tool when you are actually doing your translations. If you can figure out how to move one coordinate, you can just mimic it on the grid with the other ones. I mean, think about this. If it's +3, -3, what you're really just doing is moving to the right 3 and down 3. So from the x's, you'll either be adding or subtracting. That's if this is a translation. You're either going to be adding or subtracting, which is going to move you left to right, or you're going to be on the y values adding, subtracting, which is going to move you up or down. Anyway, let's check this out. So if I take C, which has 2 for the x, and I do 2 plus 3, I'll get 5. And then if I do 1 minus 3, I'll get -2. And if you go take a look at that coordinate, it is at 5 and -2. So you don't really need to do the mapping for all of the points. What you need to do is the mapping with enough of it that you get an idea where the figure is going to be, and then you can just connect the rest. So like A to D, we're just going to go down 3 units. Okay, and then once we have that, we can go ahead and connect. That's your picture. Here's a neat question that we have underneath it. Write a mapping to return the image to its pre-image. So write a mapping that's going to take you from the green to the red. All right, so for that mapping, you're really just going to undo the operations that you see in the mapping at the beginning. So if the x's are increased by 3, then what we're going to want to do is decrease them. So adding 3, move them to the right. If you subtract 3, that's going to move it to the left. For the y values, you'll also just do the opposite. Okay, so if you're subtracting 3, what we'll do is go ahead and add on 3, and that will take it back to the spot where it was. The second transformation that we're going to look at in this video is reflections. Usually when we describe a reflection to each other, we might describe it as flipping an object over. We do that, and that's not a bad idea to describe it. It seems to make sense to me. The definition that we have here is a reflection is a transformation that uses a line like a mirror to reflect an image. Okay, this definition works a little bit better than just describing it as a flip, because it also starts to instruct us on how we can make a reflection on a coordinate grid. Okay, so in the picture, what we have is we do have a line that we're using like a mirror. It's called the line of reflection. That's going to be line M here. You have the figure ABC over here, and this is going to be the pre-image. Okay, and then you've got the image that has the primes on it. Okay, so we might describe it as taking that figure and then flipping it over to that spot, sort of like you're scooping up a pancake and flipping it over. Okay, but the definition is going to talk a little bit more of it as being like a mirror. I guess that makes sense with like your reflection in a mirror. Okay, and if you had to graph this, so we don't got a coordinate system that's behind it, but we will. We're going to do some problems that are like that in a little bit. So if you had to do that, here's how we use that line. Okay, imagine that we don't have the first figure. That one's not there yet, or we don't have the image. We don't have the new one. We just have our first figure there. What we're going to do is look at how the individual points compare to that line. So like in translations, don't worry about the whole figure. It's almost like a distraction if you do that. Just look at the individual points. So I'm going to look at point B. Okay, and I'm going to compare the distance that B is from that line. It should be right there. Okay, now all this is going to be measured perpendicular. Everything is perpendicular to that line of reflection. Okay, but I'm going to look at the distance that B is from the line of reflection in a perpendicular direction, and if I just extend that exact same distance across through that line of reflection to the other side, then that's going to plot the location of B prime. Okay, so whatever that distance is, make sure that this is the same thing here. We then do the same thing with C and C prime. I just went ahead and drew it all the way across, but you'd be taking whatever that distance is and make sure it's the same distance that we have on that side. And then can't really show you A and A prime without drawing on top of it, but you know, you take a measurement, whatever it is, then you use that measurement to plot directly over there, and that's how you can graph these. So you don't need to worry about the whole figure, just focus on the coordinates. And you might not even have to do all the coordinates, just enough of the coordinates that you can then reflect it and connect what you need to get your image. In example number 1, we're actually going to be doing 2 problems. We're going to be taking triangle ABC, which has these 3 coordinates here, and we're going to be first reflecting it over the line x equals 2, and then we're also going to be reflecting it over the line y equals 3. Okay, so let's go ahead and get these plotted, 2 different graphs, and then we'll take a look at how we do those reflections. All right, so for the first one, we're going to be reflecting over the line x equals 2. Okay, so x equals 2 is a vertical line. It's a vertical line that passes the x-axis at 2. So that's going to be right here. Try a different color and see if that shows up on the grid. Okay. All right, so we're going to be reflecting over that line. Now, one thing that you're going to notice different about this versus the picture that we had up at the top. Oh, and again, I forgot to answer a certain question, so I'll go ahead and do it right now. In this picture, is a reflection an isometry? The answer is yes, it is. If we maintain the distance away from that line of reflection to get to the next point, then once you end up connecting all these together, their distances between them will be the same as the distances that you had here. So this one is an isometry. All right, so different than that picture that was up there, the line of reflection is actually going through the figure. But if you treat all of these as individual points that you're going to reflect over it and then you connect at the end, it really isn't a bad thing. It doesn't have to be as confusing as it could. Okay, take for instance this point here. I believe, yeah, that was point A, but it doesn't really matter. We just take this point. You look at how it compares to the line, right? Don't look at anything else. Just look at that point and say, look, it's 1 unit to the left. Okay, so my reflection is going to put it 1 unit to the right. It's going to be sitting inside the figure. Okay, but only focus just on distance and reflecting. Okay, this point is 3 units away, so I'm going to have to go 3 units away to the other side. This point is 1 unit away, so it's going to reflect 1 unit away over here. Okay, and yeah, if you look at all of them right now, that starts to look like a little bit of a mess because the points are just scattered. But look, we plotted everything that we need so that we can connect them and get the reflection. Now, if you attempt to do all this with just the shape, it is a bit confusing, so I really suggest just do individual points, and there you go. And if you can do it in different colors, that's a really good idea too. I highly recommend that you use different colors for all kinds of stuff in a math class, but definitely when you got figures on top of figures. And then if you really had to, you don't need to here, but if you had to, you could say that your red color is your pre-image and your green is your image, and then that creates a little key for you instead of using primes. All right, for the other, look, if x equals 2 is a vertical line through the x-axis of 2, then y equals 3 is going to be a horizontal line passing through the y-axis at 3, which is going to be right here. So this one's a little bit different too. Okay, the line of reflection does not go through the figure. However, it does make contact with one of the points. All right, so this point here, we'll just go left to right. This point is 1 unit below the line of reflection, so we're going to move it up 1 unit. We'll move it up 1 unit past the reflection. This point is 3 underneath it, so we're going to move it 3 above. And this point is on the line of reflection, which means it has a distance of 0 from the line. So it's going to maintain a distance of 0. Okay, whenever a point is on the line of reflection, it just stays there. The other picture, you can even look at that and notice that there's a spot. I think there's 2 spots. 2 spots that the line of reflection goes through the pre-image, which means that those points stay there when you do the flip. So that's right here. It just didn't end up being the actual vertices, but you'll see that those corresponding points end up staying there. Let's graph an image across a diagonal line. Let's try that out. We're going to be using just a segment, which means it only has 2 points that are connected together, so CD. Okay, and here's the locations of C and D. C is at -2, 2. I'll go ahead and plot that one. Actually, since it's my pre-image, I'll make sure that I try and stay consistent here and use red. D is at 1, 2. All right, so there is our pre-image, just a little segment. For this, I am going to go ahead and add in the letters because I know I'm going to want to reference them when we get there. Okay, so there's a segment called CD, and we are going to reflect it over y equals x, and that is a diagonal line. Now that is what we call the parent function to all linear equations. It is a line that is going to be passing through the origin, so it has no shifting up or down from there. It starts right at the origin, and it's got a perfect slope of 1. I mean, really think about that and how it compares to y equals mx plus b. You don't have a b value, so that puts you at the origin, and your coefficient of x, what would be the m, is a 1, so you have a slope of 1, up 1 over 1, up 1 over 1. Okay, so if you've not learned already, you need to that. See if I get this line up as perfect as I can. That the line y equals x is that line. Okay, you need to know that one. It's incredibly important for other stuff moving forward when you get into Algebra 2 and any of the other courses beyond here. There's a concept of inverse functions and inverse relationships, and knowing that line and knowing how to reflect around that line is crucial. So this one is really important. It's not just something that we're covering in geometry. Okay, so what is that going to look like when it does reflect over? Okay, when it does reflect over. All right, with these points, you got to be careful that you don't do maybe a vertical or horizontal type flipping, because the line isn't vertical or horizontal. So these aren't just going to flip over. D is not going to end up being right here, and C is not going to end up being right there, and you have a line in that direction. You want to consider the individual points and what their distance is from that line of reflection in a perpendicular direction. Okay, so I'm going to take a ruler here and line it up so it appears to be in a perpendicular direction, right? So if I draw a line here, I'll get a perpendicular line. And now I'm going to go all the way over to D. So when you look at D, it's not about following so much the grid lines that get you to the line of reflection, but it's looking at how far it is in a perpendicular direction. Okay, so it's like part of a diagonal of a box. So D prime is going to end up over here. That's where it's going to end up, a little bit lower. Now you can still use the boxes to count like over and down and things like that, but you really want to be thinking perpendicular at the same time. So there's a lot of thoughts that go into them depending on what shapes you're working with, but one definite clear way you can work on it is to think of it as perpendicular. So now if I'm looking at C and I want to make a perpendicular, that's going to be, so I see a square shape here. That would be across the diagonal of that square, okay, which is 2 and then 2. So if I do that again, 2 and 2, that's going to give me C prime. And of course, when I connect D prime and C prime together, I'm going to get a segment that is the same length. It's still length of 3, But it's kind of interesting here that you start with the horizontal and then you end up with a vertical. Now, I can't really show it here on the computer paper that I'm using, but you can do this yourself. You could go ahead and fold along that line of reflection. Maybe you can imagine as they're folding over, okay, and test it out. But fold it over and see that these points do fold over onto each other. Okay, a really good way to work with reflections, whether they're diagonal lines or, even if it's the last two examples that we looked at, you can do like a fold. Keep folding back and forth, flipping the paper to see if your answers are looking good. When doing reflections in the coordinate grid, there's 4 particular lines of reflections that we want to know mappings for. Okay, now you can reflect over any line that you want, any horizontal, vertical. You can create any line, y equals mx plus b, and you can reflect over it, though that is somewhat hard. But there are 4 particular lines of reflections that we want to know mappings for. Okay, and they're going to be reflecting over the x-axis, reflecting over the y-axis, reflecting over the line y equals x, which is the one that we just did up here, and reflecting over y equals negative x, which is a lot like the one that we did here, except that you've got a downward slope. It'll be a down 1 over 1. All right, so first we're going to take a look at reflecting over the x-axis. Suppose that we start with any point AB. Any point AB, if you were to reflect it through the x-axis, what would that coordinate look like? Okay, now the neat thing about this is there is a really easy way to take the numbers that you have in the coordinate and change those so that they become the new location of the point. Okay, now what we're going to do is investigate it. So we're going to go up to this empty graph that I had here, and we're just going to make up any point. Bad points would be anything like a 2, 2, 3, 3, 4, 4, something like that. That is, where the 2 coordinates are exactly the same thing. So we want to choose something that might be more like this. Let's say that we got 4, 1. Okay, so you got the coordinate 4, 1. And if I'm going to reflect that over the x-axis, here's the x-axis. If I reflect it over that, what I'll do is just take the distance that that point is from the x-axis and move it to the bottom side, right? So it's 1 unit above, it's going to go 1 unit below, which would give me the coordinate 4, negative 1. They give me that coordinate. So we notice here that when we do that, the numbers really haven't changed. You still have a 4 and you still have a 1, which means you would still have an A and still have a B, except that you have one difference in here, which is that the Y value has actually become its opposite. So our mapping is going to be a negative B. So if you know you're reflecting over the x-axis and you got all the coordinates, all you have to do is just take the opposite of your Y value and you've got all your coordinates. Okay, what happens if we're reflecting over the y-axis? Okay, suppose we take the same point here. If you reflect it over the y-axis, you're going to go this direction. You're going to count 4 units towards the y-axis and then continue 4 units that way, which would plot you at this point. And that point is going to be negative 4, 1. Okay, so you'd end up here. That'd be negative 4 and 1. So again, the numbers really haven't changed much except for the fact that the x has become its opposite. Okay, so if you take any point AB, reflect it through the y-axis, you're going to get the opposite of the x value, and you're going to keep the y value, so it'd be negative A, positive B. All right, reflecting over y equals x is the ones that a little bit, I don't know if they're trickier. I mean, once you figure them out, they actually save you a heck of a lot of time versus what we did to reflect the image here. All right, so let's go ahead and draw a line just so we have one. The axes are easy to look at because they're there. They're pretty bold. Okay, so we're reflecting now over y equals x. So here's that point, which is going to be at 4, 1. Okay, when it reflects over, what I had done is talked about perpendiculars as you go that way, right? So I would need to go like a full box and then half a box. So I do half a box and then a full box. That would get me to the new location. But you can always be thinking about folding as well, folding things over. And you might even notice that if you were to fold along that line, these two parts of the axes are going to match up. All right, so say I went 5 units out on each one. That point and that point, they're going to match together when they get folded. All right, so now I can maybe do a bit of a comparison with, well, how far is that point from the x-axis? It's 1 unit in at a distance of 4 from the origin. Okay, so then that point's going to be 1 unit in with a distance of 4 from the origin. Okay, a lot of imagination going into this one to figure it out where it is, but it's going to end up at this spot, which is the coordinate 1, 4. And what we're trying to do here is come up with a mapping so you don't have to do this all the time. That you can just use the mapping and then say, if I'm reflecting over y equals x, what does it look like? And here's what it does. It takes that coordinate. It doesn't make anything negative in there. It actually switches them. The x becomes the y and the y becomes the x. And that will be true for any reflection over y equals x. Okay, they just switch the order. We can even take a look at this picture and verify it. Let's just take C. That was at -2, +2. It was at -2, +2, which means that C prime is going to be at 2, -2. Out 2, down 2, and there it is. So now that we have that mapping, it's going to make it a lot easier to do. All right, last, y equals -x. Okay, so for that one, that is, I always call it the other diagonal. I think that's a somewhat fitting name for it. Okay, so it's the other diagonal. It goes in the downward direction. If you're going to fold it, that might be the easiest way to do this. Imagine folding it. This axis and that axis are going to come together. So I've got one point to the outside at 4, so 4 out, and then to the outside. So here's going to be 4 down and to the outside. So just kind of imagine that. Keep thinking about it folding and how the axes are going to match up, and then those points would be on the outside, so they go with each other. Okay, so what is that coordinate? We got -1, -4. They're actually both negative numbers here. We're in quadrant 3. Okay, now a comparison to the original coordinate, you're going to see two things. Both of the numbers have become negatives, and they've also switched places with each other. So that means that our mapping over y equals -x is going to give you a -b and a -y. Sorry, -a. And now the great thing is, if you know those mappings, more importantly, you'd want to know these two. Now, I said that this one's going to be really important for other future classes. For right now, though, these end up being the two that you really want to probably memorize if you had to make choices out of them. The other two are pretty intuitive. You could teach yourself that like on the spot. These are obviously the harder ones to try and make sure you're in the right spot, so you want to know the mappings. And if you have them memorized, it makes it a lot easier. And finally, we're going to talk about lines of symmetry. A figure has a line of symmetry if it can be mapped onto itself by reflection in the line. Okay, what does that mean here? Normally what we do is we talk about lines of symmetry as if you could draw a line through the figure, does it cut it in half? Can it fold it onto itself? And that's a great way of doing it. Okay, like in the first picture here, I believe we got 2 of them. Hopefully I get the first one in the right spot. It's sometimes hard to estimate the middle. But if I drew a line here, that looks pretty good. If I drew a line right there, that would be a line of symmetry. And the way that we normally know this, like way back in elementary school, is that if we fold it along that line, it's going to match up with itself perfectly. Now the definition that we got, little bit more technical on things, but it tells us the same thing. It's going to reflect onto the image, or the figure is going to reflect onto itself when it goes through that line. So that means that, like if I took this point and I reflected it through the line, it's going to end up where that point is. And if I take this point and I reflect it through the line, it's going to end up where that one is. If I take the point that was here and reflect it through the line, it ends up where that one is, and so on through all that. So you literally take everything that would be, in this case, on the right, and when it reflects, it becomes the left side, and everything that's on the left, when you reflect it, becomes the right side. Now that picture has another line of symmetry. You can also call them line of reflection, so if I go back and forth between the words, it's okay to do that. All right, so the same thing can be done here, just goes up and down. So that one actually has 2 lines of symmetry. All right, so how many lines of symmetry does figure B have, and how many lines does C have? Horizontal. Picture B has a lot of them. It actually has a total of 6. Tried to color code them here. The purples are all going through the sides, sort of like the vertical one that I had here, and then the green ones I've got going through the vertices like I did in the horizontal one that's there. But you got, it looks like there's a lot of them there, but there's actually 6 of them because you've got 3 of the purple and you've got 3 of the green ones that are in there. So some figures might have only 1 line of symmetry, some 2. Some can have a lot. Imagine what you would get with a decagon, right? You get a lot in that one as well. How many lines of symmetry do you have in a circle? That's a good question for you.
Later, blah.